Good afternoon, everybody. I will give a presentation of at least my view of what is the available density data set we have for thermosphere modeling. So this is a little bit higher, mostly you will see, and critical gaps therein. So this is an issue that we are presently discussing within the COSPAR ISWAT cluster atmosphere variability. So it is a very timely issue. This is the outline, so it is a little bit wider. The outline speaks of more than I will actually address. So here's the list of the errors that contribute to the total modeling and forecasting error in atmospheric drag, or let's say atmospheric density. Of course, when we're talking about the empirical models, it's the fact that they're simple and coarse modeling algorithms. The second point, that is the point we will speak of today, is sparseness, errors, and inconsistencies in the compiled density data sets used in the modeling. Third point is the use of proxies for solar activity and for geomagnetic or solar wind interactions. Fourth point is that the proxies that we do use and have are often of too low temporal resolution. Something that we will not speak of today either is the predictions of these proxies, which is another matter altogether. And then something what you may not think has any relation, but also errors in the satellite model actually gives you an error, or at least an inconsistency in the density data set that you derive. So like I just said, so the items 1 to 5 pertain directly to errors in the prediction of density, but number 6 also. So in this talk, I will just give you a short review of the DTM model and the assimilated and validation data that we have available. Well, by no means exhaustive, but let's say the largest and most important ones in my view. So I will not address these points in orange. So these are also data that are critical for upper atmosphere modeling, the observation of solar EUV and solar wind and geomagnetic activity. That will not be addressed here. Semi-empirical models, going very quickly. Here speaking only of DTM, but this basically holds for MSIS and JB as well. They are low resolution models, but they are easy and fast in use. So that's why they're used, for example, in orbit computations and operational orbit predictions. They are relatively accurate, depending on the scales you're looking at. But so they are climatology. So they give a specification of climatology. Most of the models, they give temperature and constituents using a fixed temperature function, and then variations are modeled using spherical harmonic function G in this case. And then, like was explained in the last talk, we can compute the total density as the sum of the individual constituents because we're above the turopause. Here's just a quick example of how well or not well we reproduce densities. If you look immediately, I hope you can see my mouse here. If you look at this left picture, bottom zoom, this is just one revolution of densities of the GOES. That's how we said it in the past, so I'll stick to GOES. So you have the measurements in blue, and then you have the 3 CIRA, the COSPAR reference atmosphere models. In green is MSIS, in pink is JB08, and in orange is DTM. So this is about what you get when you're predicting these densities. You will also see that there's a spike in the observed densities of about 25%, whereas there's essentially no geomagnetic activity. That is the kind of resolution that we cannot reproduce with the semi-empirical models. So I'm not speaking about the GCMs here. So the data used specifically in the construction of DTM is shown here. So you see here on the right the most recent period where we had the accelerometer missions, Grace, Champ, GOES. And then we had old geodetic laser satellites at higher satellites, but so you can easily see that we have high resolution measurements, but even in this last 10 to 20 years, it is very sparse, below 250 kilometers, above 500 kilometers. And we actually do not have a lot of precise measurements during solar cycle max. Then you see we have a solar cycle 23 essentially without any good measurements. So a hiatus in the middle. And then we end up in cycle 22 where we had all the spectrometer data in blue, specifically Atmosphere Explorer and Dynamics Explorer. Problem with these data is there are some issues with instrumental bias. The satellites were in eccentric orbits, DE2 at least. It was before we had measurements of EUV, so we don't have the good drivers. So it's not recent, and so it's also very difficult to, if you want to reprocess or edit this data, it's a little bit complicated. Down in black, in the past also, we had accelerometer inferred total densities. So a cactus, which is a little bit high, then we had the MESA on the Atmosphere Explorer CNE, and these are actually pretty low altitude, and the Air Force CETA 2 and 3 data sets we have as well. Here we have the same thing, bias and scale factors. We don't know exactly how these were computed, and we don't know exactly what kind of satellite model was used. So when we are modeling and we're trying to fit the model coefficients in a new run for DTM, all the items, the listed items that I've shown, so 2 to 4 and 6, they all have an impact on the model. If you look at this diagram, it shows you that to create a model, a new version of DTM, we're using solar EUV data. Actually, we're using the solar radio flux. We use geomagnetic data, KP, or the new index developed by GFZ HP, and then we have density data. Now, the solar EUV and the geomagnetic input we use as is, so we consider it truth. Whereas in recent developments, some people are also adjusting the drivers. So this is something I do not adhere to, but this is the reason, one of the reasons why. You can see here a plot of 5 different versions of solar EUV drivers. We have F10.7 in black, F30 in blue, and then we have 3 different versions of S10, which is essentially the helium-2 line used in JB08. They're all expressed in the same F10.7 scale, and you see this for the year 2012, the range of activities that we could use. And of course, if you use this pink line or a blue line, your model is not driven at all in the same way. Same holds for KP and HP, of course. Now, the density data, on the other hand, we do apply editing, either thresholds or some 3 sigma editing or something. We can select the data, so based on specific periods in solar activity, or we're eliminating periods where instruments had higher noise, and we can apply scale correction. So at the bottom right, you can see an example of a scale correction. Here's a comparison between the ESA GOES data and the GOES data as predicted by the US Air Force has the model. Difference in these densities, essentially we see the same variability, but there is about a 20% difference. So, and that is due to the satellite model that is used. So very, very simple. Of course, this is just an example. Suppose we only have the blue data sets, and so we have a density only around medium solar activity. When we assume a linear relation with the solar activity, and we're trying to estimate model coefficients, and we only have a very limited range of a specific parameter, then of course model errors will be introduced due to sparseness of the data. If we had like the red, the blue, and the green, we could have a an excellent fit over the whole solar activity range. If you only have one of the three, we will have some kind of model bias at either low or high or both solar activities. Same holds, of course, for diurnal and semi-diurnal variations, where you have to fit a sine wave. So you need to have sufficient data as a function of local time. Let's skip this quickly. This is just the most recent high-resolution data we had came from these 3 accelerometer, basically gravity missions on the left, even if CHAMP was also a magnetosphere. But what you have to realize here is that these are actually all data of opportunity. These were missions that were never designed to provide a thermosphere data set. And unfortunately, a lot of people did process them to thermosphere densities, and a lot of progress was made thanks to these big and complete data sets. Now, the effect of the sparseness can be seen in the following set of examples. So what you see here is, for example, for GOES, upper left, you see GOES was in a near sun synchronous orbit. So all our measurements are actually between 6 to 8 a.m. p.m. time frame. Secondly, left bottom, you can see that all measurements were under low to barely medium solar activity. And at the bottom right, you see that we only have a few days of data below 200 kilometers. And that is the only data set we have of data below 200 kilometers for a very, very long time. So here's DE2. Upper left, what you see is the gray is the density, is the molecular nitrogen measurement as a function of altitude. And then on the right axis, you see the local time. So you see we have about 3 complete 24-hour periods over this 3-year period of DE2. At least it looks like this. In reality, data are often cut off at a specific altitude. For example, I cut it off at 400 kilometers. Above that altitude, the data gets too noisy. And so here we actually do not have complete solar local time coverage. And you can see that on the bottom right, you see that due to the elliptic orbit, so this is the kind of coverage you have as a function of altitude and latitude over a 2-week period. And so, of course, if you have this kind of distribution, it is very difficult to estimate, to decorrelate latitudinal, altitude, longitude effects and temperature profiles. Everything is mixed in together.
Sean, there are 2 minutes left about.
Oh, okay. Here are some examples as well. So you see cactus is only low latitude. URs, which is actually not sun synchronous, is also measuring only in a specific local time frame. Here we have the CETA accelerometers, sun synchronous, short data sets, but we have data below 200 kilometers. So here's one data set where we have actually total densities below 200 kilometers. Here's a second pair of data sets where we have measurements below 200 kilometers. But again, here we are bothered by the fact that MESA C has an elliptic orbit. It's about 1 year, only low solar activity. E-MESA is a low inclination orbit, as you can see in the green. This is quickly a comparison of the model with these low altitude data. You can see that essentially at these revolution time spatial scales, it is not too bad. There is sometimes overestimation, sometimes underestimation, but it always within the more or less 10 to 20% as expected. Here I quickly compare DTM 2020 on the left and NRL MSIS on the right, starting at 120. So it's latitude versus local time. 120, 150, 200, 220, 250. Just to show you the differences between these two models. And you would say, well, these differences are pretty big, which is true. The structures are completely different, even if the difference on average is still within that about 10%. Now, since John is online, I hope he agrees with me, is that in this altitude range between 120 and 200, 250 kilometers, DTM is essentially extrapolating data from higher altitudes down to this 120 kilometers bottom altitude, whereas NRLMSIS is a more complete, a little bit more sophisticated empirical model, and it actually has data from the surface upwards. And so the information that is in NRLMSIS is not based on the same data sets as in DTM. So NRLMSIS is based on few but actual data in that altitude range, radars, rockets, and such, whereas DTM is only based on these few days of GOES, let's say below 200 kilometers. There's nothing more below 200 kilometers in DTM. So what you see here is the impact of not having any data between 100 and 200 kilometers, which is, as you can see, pretty important. Just to give you a quick status, since we were talking about DTM, and it is actually being developed to a new version this year. So what you see here is a comparison with all the data sets that were used without a star, and when there is a star, it means that it has not been assimilated. So the rightmost column is the newest DTM version, and you see that for GOES, our reference was the last version of DTM 2013, so now we have made a significant improvement. If you look below the blue line, those are the data sets where there is a portion of the data below 200 kilometers. What you can see there is that, as expected, NRLMSIS is doing better with MESA and SETA, and I think, so John can correct me, I thought these data were actually assimilated in NRLMSIS. Then there are two other points that you can see here. You have the high precision data in green, so GOES, for example, and low precision observations in red. And if you look at the data below 200 kilometers, you can clearly see with GOES you reach the order of 9%, whereas with the MESA and SETA you're of the order of 15 to 20%. So there's clearly also an issue with the quality of the data. So we need much more accurate data than we have till now. So any news and updates on this modeling effort is on this website, also on the HP geomagnetic indices, by the way. So the new DTM will come out this fall, the whole atmosphere model, since we are working on a model this time from the surface up by combining two models, so DTM at the top and the UK Met Office model at the bottom, with a transition zone, will be released in December 2020. And this new whole atmosphere model, MCM, hopefully will be, of course, more accurate also in the 100 to 200 kilometer altitude range, despite the fact that we don't have a lot of validation data in that region. So in summary, so we had a simple and coarse modeling algorithm. So basically what I don't think this is the limiting factor yet. So what we've seen, typically the GOES versus the MESA and SETA data, we are still limited partly also by the quality of the data itself. The model can be fit to 10%. Most of the data is not at that precision level. Sparseness, errors, inconsistencies. So yes, definitely more data is needed, and accurately processed. So calibrated, satellite model, aerodynamic coefficient and such. So of course, I'm preaching to, but Daedalus is, of course, will be of great help. Also, if you see that we had essentially no total densities below 200 kilometers. The proxies we used. So issues with the solar EUV data. Yes, we have those. There is a issue with calibration, especially with the space-borne instruments. Some colleagues think that the geomagnetic indices are not that good because they're global proxies. That's why I put them in orange. I do not agree. So it's something like the green and red. And so I put it in orange. I don't think it is a major problem, not for our kind of thermosphere models. The resolution of the proxies can be increased if we have more instruments, typically if we are measuring F10.7 or F30 in both Canada and Europe, which will soon be the case, I tell you. It will probably be measured in Poland soon. We will have 2 measurements per day on solar radio flux. And there is also, like I said, this geomagnetic proxy HP, which is instead of 3-hour cadence, it's an hourly geomagnetic index. Errors in the predictions, well, it can be improved for solar proxies, but for geomagnetic activity, the horizon will remain very, very limited. Errors in the satellite model is for recent spacecraft. Shape and mass should be modeled correctly. It should be possible to model it correctly. Of course, for debris, that is a different story. We do not always know what it looks like. And second point is we do not have a standard on how to compute drag in the community. So thank you. Sorry for taking a little bit more time. That was it.
Yes. Thank you very much, Sean. Very interesting presentation. So there are a few questions in the chat, and I think we should go very shortly through. So what you discussed, Sean, was that you think that a few very accurate observations are more valuable than many more non-accurate observations. John said that the MESA and CETA data are assimilated in EMSIS. So has that also been his impression?
My impression?
Yeah, no, John's impression, if we want to say short words about it.
I'm sorry, Claudia, could you repeat your question?
Yes, so I was wondering, Sean said that only few data with high quality is even more valid than more data with low quality.
Yeah, it's yeah, that would be valuable. I mean, certainly the Daedalus will help us with our EMSIS development, and we're going to have a few words to say about that. We actually have a EMSIS 2.0 that we're getting ready to release in the next couple of months, and we'll have a few words to say about that in that paper.
Okay, yeah, good, thanks. There are other questions. If DTM will be available to everyone, will be open source. Is there a short answer to that?
Yes, it will be available. No, it's not open source.
Okay. Then there's a question by William, and the question about open source was asked by Armin. William asked about if also other data from lower altitudes, I guess, like timed and Saber and tidy are used to define the lower boundaries. And if ground-based observations are intended to be used, has been asked by Sempet.
Well, ground-based, no, not anymore. Like in DTM 2000, I did use the ground-based data. I'm not using them anymore because I'm having troubles with the, for example, radar temperatures. I'm not as comfortable using those as they are at NRL. And the other point is, unfortunately, the temperatures that are measured by, is it GUVI, are good till about 105 kilometers, and our model bottom is at 120. And 120 kilometers, there are actually grids measured, but they're very bad, so you cannot use them. So we're just at that altitude where we have nothing. A little bit below we have measurements, and above we have measurements, but between 105 something and 200, we have essentially nothing.
Okay, good. So we're looking forward to new data.
We do.